Hi guys, I'm Alexia Vanner Espermo. You can call me Sia, and welcome to another episode of MedSci. For today's episode, we're going to discuss about the magnetic properties of materials. So, let's get started. Why do we have to study the magnetic properties of a material? Magnetism is the phenomenon by which materials exert an attractive or repulsive force or influence on other materials. It has always been present in our daily lives. What do generators, transformer, motor, credit cards have in common? Answer: magnetic material. Present in countless tools of modern life, these materials, because of their importance and complexity, make research on magnetism intense nowadays. One of a familiar example is a compass, in which a magnetic compass needle lines up with Earth's magnetic field that is used for navigation. Which means that in the presence of an H-field, magnetic moments within a material tend to become aligned with the field and to reinforce it by virtue of their magnetic fields. This equation means that the magnitude of magnetization is proportional to the magnetic susceptibility. Magnetic units may be a source of confusion because there are two systems in common use. The units for both systems as well as the appropriate conversion factor are contained in this table. The macroscopic magnetic properties of materials are a consequence of magnetic moments associated with individual electrons. In this diagram, each electron in an atom has a magnetic moment that originate from two sources, an orbiting electron and a spinning electron. Bohr magneton is the most fundamental magnetic moment. There are three types of magnetism: diamagnetism, paramagnetism, and ferromagnetism. It is found in all materials, but because it is so weak, it can be observed only when other types of magnetism are totally absent. It is displayed in the transition metals like iron, cobalt, nickel, and some of the rare earth metals such as gadolinium. Now, let's discuss the two subclasses of ferromagnetism. In this diagram, we could see the anti-parallel placement of spin magnetic moments in the manganese oxide. This phenomenon is called anti-ferromagnetism. The phenomena wherein the material exhibit a permanent magnetization is called ferromagnetism. Cubic ferrites, hexagonal ferrites, and garnets are ceramic materials that are ferromagnetic. For ferromagnetic, anti-ferromagnetic, and ferromagnetic materials, the atomic thermal motion counteracts the coupling forces between the atomic dipole moments, causing some dipole misalignment, regardless whether there is an external field present. With increasing temperature, the saturation magnetization diminishes gradually and then abruptly drops to zero at what is called the Curie temperature. Anti-ferromagnetic material is also affected by temperature. This behavior vanishes at what is called the nil temperature, wherein the anti-ferromagnetic material that have temperature above this point becomes paramagnetic. Now, let's talk about domain and hysteresis. Hysteresis behavior and permanent magnetization may be explained by the motion of the domain walls. But first, let's define domain. Any ferromagnetic or ferromagnetic material that is at a temperature below Curie temperature is composed of small volume region in which there is a mutual alignment in the same direction for all magnetic dipole moments. This is what we call the domain. Arrow represents atomic magnetic dipoles. Within each domain, all dipoles are aligned, whereas the direction of alignment varies from one domain to another. Now, how does hysteresis happen? The resistance to movement of domain walls that occurs in response to the increase of the magnetic field in the opposite direction accounts for the log of B with H or hysteresis. Both ferromagnetic and ferromagnetic materials are classified as either as soft or hard on the basis of their hysteresis characteristic. So, let's discuss the difference between these two. Alloys composed of irons are soft magnetic materials that are used in generators, transformers, motors, dynamos, and switching circuits. This is a schematic diagram for soft and hard magnetic materials. Within the past few years, magnetic materials have become increasingly important in the area of information storage. In fact, magnetic recording has become virtually the universal technology for the storage of electronic information. When the gap is cut, data are introduced by the electrical signal that generates magnetic field that magnetizes small area of the disk within the proximity of the head. This picture shows how information is stored and retrieved using a magnetic storage medium. Hysteresis loops for this magnetic storage media should be relatively large and square. These characteristics ensure that storage will be permanent. There are materials that displays a behavior in which resistivity at a very low temperature abruptly plunges from a finite value to one that is virtually zero and remains there upon further cooling. These materials are called superconductors. It is a temperature wherein the material attains its superconductivity state. This phenomenon is known as Meissner effect. On the left side of the picture, the superconducting state excludes a magnetic field from its interior. While on the right side of the picture, you can see how the magnetic field penetrates the same body of a material once it becomes normally conductive. Type 2 superconductors are preferred over Type 1 for most practical applications by virtue of their higher critical temperature and critical magnetic fields. That's it for today's episode on magnetic properties of materials. I hope you guys learned a lot from this video. Don't forget to click the subscribe button down below. And I'll see you guys next time. Bye!